Hello, so we're just going to go through a Year 11 final exam paper, and you can use this to practice some questions or review the questions you did in the exam. Let's have a look. First is multiple choice. So, which of the following is a heterogeneous mixture? That means hetero, different. Okay, so we're looking for different particles. That's going to be salt and pepper. 2. Experiment was carried out. You can pause it if you need to be and read through it and do it yourself. Right, okay, so an experiment was carried out in a sample of gas. The temperature, volume, and pressure was recorded, so temperature is the same. As the volume goes up, pressure goes down. So, which of the following, so pressure and volume, if you remember that. Now, if you think of an example like a syringe, okay, if you press down hard on that, the low pressure, low volume, well, let's compare these two, right? This is volume, low volume would equal high pressure, right? And here we have high volume equals lower pressure comparatively. So if you were to have a graph, okay, so pressure is high, volume is low, volume is high, pressure is low. Okay, this is Boyle's law. I always think of the Boyle pimple. Yeah, anyway, so there we go. Let's have a look at three balanced reactions. So you can pause it and have a read of this. But we've got 3 reactions, and they just want to describe each of these. So the first one, let's see what options we've got. We've got synthesis, precipitation, or combustion. So you could think of this as possibly, most likely A, because it's 2 things coming together. A plus B gives you AB, that's a synthesis. Let's have a look at 2 though. Here we've got aqueous solutions, and then we end up with a precipitation. So that's a good precipitation. So chunk, 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 chunk. And here we've got an acid plus a carbonate. So which is all 3 of these? 3A. Ammonia reacts with oxygen to produce an oxide. So we've got, it's a balancing issue, and we don't quite know what this is, but we can figure it out. What do we know most about? Well, let's start off with hydrogen. Here we've got 12. How many would we need to have 12 here? We'd have to have 6 times 2 equals 12. So Z is going to be 6. So the question is then, all right, now if we're looking at nitrogen now, there's 4 nitrogens here, and therefore we would need 4 nitrogens. Okay, so let's have a look. 4, and that would have to be 4 So that would mean this one. So that's the only one really with both of them, but let's just check. So if Y is 1, that means how many oxygen would we have? That's going to be 4, right? So 4 times 4 plus 6 is 10. And now 5 and 0. 5 times 2, sorry, is 10. So that double checks for C. A chemical reaction proceeds from reactants to products. Enthalpy change is constant. Right, well, think of combustion. We went through this. So if you have combustion, okay, and it's complete combustion, you can think of that as like C, right? But if you had incomplete combustion, and you went to something like carbon monoxide, and then later on you combusted the carbon monoxide completely, you'd have like the change in enthalpy, that A plus B equals C. And conservation of energy is going to be Hess's law. The molecular structure, let's have a look at that one. All right. Well, we could put a symbol here for like black and white. So let's have a look. So black, white, white 2 gives us black 2, white 5. Alright, and then you just want to know what X, Y, Z would be. Alright, so well, let's try doubling it. Okay, so 2. And that would be W4, but see the 4 is not enough, 4, and then you got 2 there. We're not going to get to, we're already past 5, so let's, in this case, let's double everything, right? Try again. 4. Okay, so let's just test it out with a 4. And then this would have to be a 2, right? Because we're looking at the black first. So you've black here, we would have 4. Black here, we would have 4. White, we would have 8 plus 2, which is 10. And white is 2 lots of 5, which is 10. So if that's 4 and that's 2, and then this, we just leave this as 1. Where is it? 4, 1, 2. There we go. How many oxygen atoms are present in 10 moles? So when you see this, oxygen atoms, you think of Avogadro's number, 6.022 times 10 to the 23 particles in any mole of substance. Now we're looking here though, they're talking about oxygen atoms. So there's 2 atoms per mole of this molecule. So we've got to times it by 2. And then they're saying that there's 10 moles of the molecule to start with. Okay, so let's have a look. Well, let's just do this bit first. So that would be 6.022 times 10 to the 24. And then that's times 2. And then that double it, that's going to be 12.044 times 10 to the 24. But we don't write it in that form. We've got to move the decimal. That's 1.20 times 10 to the 25. Alright, which of the following is the correct subshell notation? So we're just looking for any errors. Might as well start with the easiest one here. Fluorine is group 7. 1, 2, 3, so that's 7. Okay, we'll come back and check this in a sec. Chlorine that's also group 7, so that's not right. Bromine is also group 7, that's not right. And sulfur is group 6, 1, 2, 3, 4, 5, so that can't be right. So it's looking like this is, well, it's the only one there. If you wanted to just, that would be enough, but just to double check, remember fluorine is the 9th element, so there's hydrogen, helium, then you got the next 7 in the next period, so they're both right, so it's correct. 8A. How much water would you need to be added? So this is a dilution question. What are we going to use? Concentration, CV, final, initial. Alright, so it's just a matter of, now you can leave it in milliliters here, because but just be careful because we've got to answer in liters. So let's just leave it in milliliters and do that last step later. Okay, so initial concentration is 2.7 moles per liter times 650 milliliters. What is the final volume? We don't know. We're going to find that. And the final concentration is 0.5. So divide both sides by 0.5. Volume equals to, now where's my calculator? 2.7 times 650 divided by 0.5. 3518. Don't forget milliliters. That's the final volume. So how much is added? You're going to have to find the difference. 3510 minus 650 equals 2860 milliliters. Answers in liters. 2.86 liters. Here we go. All right. Have a look at that. So straight away you should be looking for your reduction values, potentials. That's not that sheet. Here we go, this one. You get your periodic table and some other data sheets. Okay, so this is standard potentials in reduction form. So let's just write out. So it's nickel and tin. And which of the following describes voltage produced by this cell and the direction of the flow? Alright, well, we can let's just write down see, I'm looking for nickel and tin. So let's just don't think too much at this stage. Just write down nickel 2 plus 2E. Nickel. You just want to double check that you got the right, because there's different forms of the same. I know that this is negative. And SN2 plus E. SN. Okay, so these are both, these are both being reduced. So the question is, one of them can only be reduced and the other one's oxidized. So which one's which? The rule is that you're going to have to flip, when you flip one of these to oxidize it, you have to also change the sign. You know, which one, I mean, the rule is it has to be positive, their overall cell potential. So which one of these can we flip and it still be positive? Well, it can't be this one, it's too small. So it's going to be this larger one. So let's rewrite this in reverse. This is now being oxidized. Okay, so this is going to become plus 0.24 volts. So we add these up. What do we get? A cell potential of 0.1. So that's one of these two answers here. Now the question is, which way is the electron that's flowing? So that we're starting with nickel, and then nickel turns into Ni2 plus. Okay, so this has been corroded. And what's happening to the electrons? They're flowing up this way, in this direction. And the electrons are forming on the surface here. And then the SN2 plus combines with the electrons to deposit tin metal. So it's going from X to Y, X to Y. So that would make it this one here, X to Y. Alright, properties. So we're looking at mystery objects, and they're asking us, like, this is about bonding types. Is it covalent, ionic, or metallic? So what are some properties of things that are metallic? They're conductive, and they can have a higher melting point. They can have a lower melting point at times. Okay, it's the metals are malleable. Okay, compared to ionic substances. Ionic substances have a high melting point. Okay, and they're brittle. Okay, molecular structures, they're not conductive, and they have a lower melting point. Okay, because the intermolecular bonds are weaker. So what's more likely to have molecular structure? Well, that's something with a low melting point. Okay, they're both lower. However, this is electrical, right? So can't be this one. So that's going to be metallic, that one. This looks like ionic. Oh, wait a minute. No, this is covalent, giant covalent type of diamond. Okay, so see, this is ionic because when it melts, ionic substances are conductive, whereas molecular ones are not. So this must be R11C. All right, let's have a look here. Right, so here we've got a mystery substance. Well, straight away, we've got an amount of gas produced at a certain volume, pressure and temperature. So alarm bells should be ringing for this constant here. Okay, amount of moles of gas at this temperature of any gas is 24.79. All right, so what do we do? Well, we're told that there's 0.607 litres of gas. Okay, and then the constant was in 1 mole, there's 24.79 litres. This is going to tell us how many moles of hydrogen gas. 0.607 divided by 24.79. 0.024, let's go 9 moles of H2. So 0.0249. That's got the same number of moles. This has got double. Okay, and this has got the same. So it's a 1-to-1 relationship. 0.024 and not 4.45. Let's say 4.5 moles. Okay, so now we think we know moles. Moles equals mass over molar mass. So we're trying to find the molar mass. We know the mass here. And now we know the moles. And because we've got this equation, we can solve for molar mass. And molar mass is mass over number of moles. Okay, so it's 1.6 divided by 0.0245, thereabouts. 0.0245, 65.3 grams per mole. There's a mole. So what's you can look up your periodic table just to check. 65 zinc. Okay. 2 significant compounds of nitrogen. What are the oxidation numbers? All right. So nitrogen dioxide, sorry. Okay, so remember when you're doing oxidation numbers, there's some rules, and the rule is oxygen always has an oxidation number of -2. So start off here, -2 times it by 2. And because this molecule has an overall neutral charge, you can say that it must, nitrogen in this case has a +4. It's just one of them. So +4 balances that out. Into 0.5. So -2 times 5 on this side gives us -10. What balances out with -10? Again, this molecule is neutral. +10 divided by 2 plus 5 is going to be those two. So +4 plus 5. Element X lies in the middle of 9 elements. Which element is most likely to have the lower electronegativity than X? So which is the most electronegative? Fluorine, and that's on the periodic table. Okay, fluorine's here. So you got a trend going this way with increasing electronegativity. Why is that? Well, it's because the nucleus is getting more protons, and so there's more positive charge that's going to attract electrons. Now, what about this direction? Now, as you go down, you get more layers of shielding from the, the shells. So you get less electronegativity as you go down because of the shielding effect of the electron shells. So you get more. The trend is increasing electronegativity in that way. So which is going to have a lower electronegativity, or something in this direction and something in that direction. Overall, that leads to gamma, which is C. '15. The energy profile diagram, R can react to form either of these two products. Compared to the reaction of R1, the reaction of P1, sorry, R to P1, R to P2 is which of the following? So when does it reach its product? Is it faster than 1, or slower than 1? It takes longer. So it's slower. Okay. Now both of these are endothermic because they're above the starting point. Which ones, compared to P1, P2 is less endothermic because it's not as high up. So that leads us to our answer. First, ionization energies. So remember, ionization energies, they kind of had that pattern. Hydrogen, helium, lithium, stuffing this up a bit. That's it. That should be higher than that, and then it repeats. Sodium, and this pattern is each one slightly lower, and so these are group 1 and think about it, you've got lithium, okay, it's not very electronegative, as in there's not much pulling power from the nucleus, and you've got your little electron there hanging out, and so it's very easy to pull this out. The amount of energy required to pull that away is not much. So that's why lithium, when you drop it in water, is reactive, because it's got what the oxygen needs. It's going to rip that electron away. So let's have a look. This first one is, so having a look here, what can we conclude? Element W belongs to group 7. Well, what out of these, because there's an order, right? This has got to be a group 1. Which makes that group 8, and that group 7, this group 2. And it goes up, up, down. So we're not quite sure where it is in this, but this is definitely group 1. So W does not, group 7, yeah, let's check. X forms ions more readily. This is a noble gas. It's not going to form ions readily. It's not really reactive. Okay, so Y exists as a gas at standard temperature and pressure. No, Y exists as a metal. That's not true. Element Z reacts with metals to form ionic compounds. No, we need non-metals to react with this. So this is group 2, they're all metals. So that can't be true. So if we go back to this first one, that must be true. It does belong to group 7. Right. Examine the 4 statements below. Which of these entropy is a key word here. So which of these we're looking to increase? So entropy is about the amount of disorder. So does disorder increase as you increase the number of particles and also the speed and movement of those particles? So going from a solid to a liquid, the movement of those particles, you've got fixed particles moving to now the particles are moving. Okay, so that's increasing. A liquid changing to a gas. All right, you're going from liquid, which is moving, but now to particles that are moving much faster, much more disorder. Entropy is increased. A molecule is broken into 2 or more smaller molecules. Okay, so 1 breaks into 2, that's increased. Reaction that results in increased number of moles of gas. Okay, so you've got more moles of gas, more particles, all of these increase. Right, the measurements below show a pattern based on the property of period elements. Okay, so we've got something here. What is that trend? Well, what's the number? We don't know what it is, but could it be atomic mass? No, because lithium, beryllium, boron, the mass should be increasing, so it's not that. Electronegativity, as we go across, it should be increasing, but here it's decreasing. No. Ionization energy, I just showed you this before. Lithium starts off, okay, and then it increases to beryllium. So that's not increasing, it's decreasing, so it can't be that. Atomic radius, hey, this makes sense because as you increase the protons, okay, and the electrons, think about it, there's more electrostatic attraction. Okay, so this pulls in, the radius gets smaller as you move across. Right. Sample of aluminium powders reacted. So this is mass. What mass? So first we've got to find out what is the limiting reagent. Okay. So calculate the number of moles of aluminium. Moles of aluminium equals 2 grams over, and you find your aluminium 26.98. To 26.98. Moles of iodine, 8 grams, and over 126.9. 126.9 times 2, because there's 2. 8 divided by 126.9 times 2. Oh. 0.0315. Okay, so find the ratio. 0.0315, 0.0315 equals 1, 0.0741, 0.035, 2.35. And now here we know that this is reacting in a ratio of 3 to 2. So let's just double check this. But times it by 3, times it by 3. So that is not a 3 to 2 ratio. So the limiting reagent is the iodine. So we are going to get 0.0315 moles. You're going to times that by 3. 315 times 3. 0.0945. Hang on. No. We're going to divide it by 3. 0.0315 divided by 3. This is just to figure out the moles of aluminium triiodide. So 0.0315 divided by 3, and then 0.0105. Now because we're finding the 3 to 2 ratio, we're going to multiply it by 2. 2 times 0.0105, 0.021. So that's how many moles of aluminium triiodide we get. And so now we want to know the mass. So moles equals mass over molar mass. So mass is going to equal moles times the molar mass. 0.021 times, what's the molar mass of aluminium triiodide? 26.98 plus 3 times 126.9. 2.21 times 8.56. That's 8.57. That is the answer. Alright, last one. The average bond energy for this equation, heat a reaction. In a reaction, okay, well, we've got standard, what is it, the delta H, standard heat of reaction is going to equal the sum of the heat of formation of the products on a sum heat of formation of the reactants. Okay, but they've given us this bond energy here, so let's just have a look. Why don't we draw it out? BR, F, there's two of those. F, and then we've got BR2. BR, and then 3 fluorine bonds. Okay, so if we have a look at the types of bonds here, 6 times 197. And let's have a look. 6 times 197. 182 kilojoules minus, so that's 192 plus 3 lots of, so that's a Br bond and F bond, 158, 192 3 minus 666 kilojoules. 82 minus 666. 516 kilojoules. I'm getting a positive for this, but I have to check this, but that's going to be the answer there. 5, 6. All right. Okay, that's a multiple choice section, and we'll just leave this as one section, and then we'll do the next part.